All right, so let's start. So this is the last section of chapter 4. So we're talking about antiderivatives. So a function f is called an antiderivative for a function um, f if on an interval I if the derivative of capital F is equal to lowercase f for all x in I. Um, the most general form of the capital of an antiderivative f on I is f plus c, since or c is an arbitrary constant. I'll kind of show you why that is. But let's actually, you take attendance, Jenny? Yep. Rip. Remind me at the end, I'll grab you. All right, so what does this mean? So let's look at the first one. So I want to find a function which derivative gives me cosine of f. So let's start with a, right? Um, I want to find a function which derivative gives me cosine of f. So what function, if I took its derivative, would give me cosine of f? Does anyone have a clue? Yes, well, let's sine of x. Let's type in sine of x real quick. So if I took sine of x here, and I took its derivative, I get cosine of x, right? So f prime of x is equal to cosine, of x. And so here, the antiderivative in this case would be sine of x. But here I'm actually going to add plus c, because notice here, if I have plus a constant, because let me show you why this is important. Let's pretend we had another f of x equal to sine of x plus 5. Well, what's this derivative? Well, this derivative here is cosine of x, right? What if I had f of x here of sine of x minus the square root of 2, right? Well, its derivative would be cosine of x minus 0, so here it's also this. So this constant just is kind of a way of showing that the antiderivative can be a whole bunch of things, right? And so in our little case here with cosine of x, we could have a cosine of x, but we also could have like a cosine plus c of x, right? Or a cosine minus c of x. And so when we take the antiderivative, we add an arbitrary constant we call c. And that just kind of allows us to say there's a lot of things that would, when we take the derivative, it will turn into cosine of x because the constant will just disappear. So if it was 5, 10, 20, it just goes away. So we just need to add this constant c here. So let's go ahead and do this for b. I want a function. So what function of x that if I took its derivative would equal to 1 over x? Yeah, so here we have ln of x plus c. So we have ln of x plus c. Okay, so here, and this is, and 90% of the time, this is what you're going to be using. Your book's going to be a little bit more clear on this. It's going to say f of x is equal to the ln of the absolute value of x plus c. And the reason they want the absolute value here, because if x was negative, right? And so another word of saying this function is equal to ln of x plus c if x is greater than 0, and x is ln of minus x plus c if x is less than 0. And the reason we have to have that, because my function, this function here can accept both positive and negative values. Log of x can only accept positive values, but if we put in the absolute value, oh, and minus 0, right? So this doesn't accept 0, right? And notice here, log doesn't accept 0. So here, if I take the absolute value of x, it doesn't matter. The domains here will match, right? And so it's just kind of matching the domain, right? So here, I have a plus c. Here I have a plus c. Here I have a plus 5, just to show that it's a constant, and here I have minus the square root of 2. And it's just to say, if I took this derivative, I get cosine of x. I take this derivative, I get cosine of x. So this plus c is just kind of generic. So in this case, we have to be kind of careful, right? So here, in order for the domains to match, we're going to take the absolute value of x. Now, 90% of the time when I work in my physics and engineering classes, we just say this, right? It's just the log, right? You skip the absolute value. It's technically incorrect. But most of the time you're always using positive values, and so that's what they do, just to be honest. But technically this is the correct one right here. So this is the correct one. So this is correct. Though you'll see this used in practice. What was I listening to the other day? One of my friends said, one of my friends is just one of the most practical person on the planet. He says, well, yeah, it works in practice, but does it work in theory? Right? I said it the other way around, right? And that's kind of what this is. ln of x usually works in practice, but it doesn't work in theory. Because you have to have the same domain. So this is the correct answer here. So this one's the correct one. Okay. Just, and your book will be picky for a little while about it. So make sure to type in your absolute value. And then here for C, if I have some function here, what function, if I take its derivative, will give me x to the n, where n's not equal to 1 because if n's not equal to, oh, hold on, that should be n not equal to minus 1. Because if n equals minus 1, we have this, right? N not equal to negative 1. If n equals 1, it's fine. So here I want a derivative equal to this. So we're kind of reverse engineer. When we take a derivative, we take n and we minus it by 1. So here we're going to take n and add 1 to it, right? Now if I took this derivative, the n plus 1 will come down, so I need to divide by it. Okay? So here, I take a derivative of x to the n plus 1 divided by n plus 1. The n plus 1 comes down, so the n plus 1 cancels n plus 1. And let me actually show you in practice. So let's say x, let's say I want to find the antiderivative of x to the 4th, right? Well, the antiderivative here would be x to the 5th over 5. Because here, if I take this derivative, which is equal to f of x, right? So I want to find the antiderivative of x to the 4th. Well, I need to increase this by 1 and then divide by 5, because if I take this derivative, the 5 comes down, so the 5 will cancel the 5, and then it's become x to the 4th. Okay? All right, so I made a table, and you'd be surprised how many times I screwed up this table to make it for you guys. I made this table for you. And so here's just it's something to have handy somewhere, right? And it's just a list of all your antiderivatives and some of the properties. So if I have so if a function and a particular antiderivative, so here's, and what I mean by particular, I mean all these antiderivatives technically should have a plus c on it. I'm just leaving the plus c off everywhere just because it gets cumbersome, right? So if I have a constant times a function, you can just pull out the constant. If I have two functions and I take the antiderivatives, you can just take the antiderivative separately. Here, if I have x to the n, the antiderivative is x to the n plus 1 over x plus the n. 1 over x is ln of the absolute value of x. E to the x is e to the x. Notice here, if I take this derivative, I get this. Cosine is sine. Sine is minus cosine. So here, if I take the derivative of this, I get negative sine. So the negatives cancel, and I get back sine of x. If my function secant squared x, I get tangent. These are just, and you know this list could go on, right? So usually, if you given a function, you know its derivative, you can just use whatever function's derivative and just flip it backwards. If that makes any sense. Okay. So here's a little table. Keep this handy. You're gonna want it. Yeah, since there's no writing, I'll go ahead and just go to the next page. All right, so let's, this page 2? What's on page 3 then? Oh, rectilinear motion. Oh yeah, I forgot. I was like, what did I do? All right, so let me go over some more complicated examples. So we did some kind of basic ones right here. And so let's do some more complicated things. All right, so here I want to find all find all functions that should have more letters on it. Find all functions, not t, but g, such that g is this. So basically find the antiderivative of this. Okay? So we want to find all functions, so we're going to have to add our plus c to this. So here, let's go ahead and simplify this. So the first thing I would do is I would do some simplification before we even do anything here. And so here we'll have 4 sine of x. Can I divide this x from here and here? And the answer is yes. The answer here is indeed yes. So here this would be plus 2x to the fourth. And then here if I take minus, this is x to the 1/2 power. So 1/2 minus 1 would give me x to the minus 1/2 power. Okay. And so what I do here, I just divided out the x. All right, now we're going to find g. So here we're going to take the antiderivative, and notice here we can do it part by part. Okay. So here let's start this 4 sine of x. Well, the 4 I can just leave, right? And the antiderivative of sine of x is, go ahead and just leave this up. So sine of x is minus cosine of x, right? So here I'll just put a negative up front and type in cosine of x. Then it would be plus 2 times the antiderivative of 4 of x to the fourth. Well, that's x to the fifth over 5. So we raise this power by 1 and then divide by whatever the new power is. Minus, here we're going to raise this power by 1. So this will be minus x to a half divided by a half. Okay. And then we have to add our plus c. And you only need to add 1 plus c at the end. So let's clean this up. It'll be x plus g equals minus 4 cosine of x plus 2/5 x to the fifth minus 2. If I divide by half, same as multiplying by square root of x. And then we just add our c, and there we go. Okay. So we can just break it apart bit by bit. Let's do it again. And this time I'm going to give us an initial condition. And this initial condition should allow us to solve for whatever the c is, right? So here we're leaving c as an arbitrary constant, but now we're going to solve for it. So let's do that one. All right, so let's go ahead and move some stuff around. So once again, the first thing you want to probably do is try to clean it up as much as you can. So this is e to the x. I'm going to add plus 20, and then I'm going to go ahead and flip this. So this is 1 over 1 plus x squared. And go ahead and write it that way. This will make it easier for us. All right, so let's do our function now. All right, so e to the x turns into e to the x, right? According to our little antiderivative chart, e to the x is an e to the x. 1 over 1 plus x squared is the inverse or the arctangent of x, or the inverse tangent of x, right? So this is plus 20 tan inverse x. And then we just need to add our arbitrary constant c. How did you get square root? Oh, x to the 1/2 power is the same thing as the square root of x. Okay. So here, if I have, so let me do this part a little slower. So 1 over x squared over x is the same thing as minus x to the 1/2 power over x to the 1, which is equal to 1 over x, and then it'll be 1 minus 1/2 minus the 1, because here I'm dividing by the 1, so I minus it out for power rules. So this is equal to minus x to the minus 1/2 power. Then from here, when I wanted to find the antiderivative, so when I took the antiderivative of all that, I need to add 1 here, so it'll be minus. It'll be 1/2 minus 1/2 plus a 1, and then divided by, so this becomes a positive half, so I put a half here, so this becomes negative x to the positive 1/2 over 1 over 2. And then here, 1 over 2 just becomes minus 2 x to the 1/2, and x to the 1/2 is minus x to the square root of x. Hopefully that should make it very, very clear how this term turned into this term, which turned into this term. It's the complicated one. Does that make sense? Perfect. All right. So let's go back to the one we were working on. Yeah, if you don't understand anything, please do ask me. That's why we do them live instead of just recording them and posting them. All right, so what do we have here? So we have our antiderivative. But now I give you an initial condition. We call this an initial condition, or an IC for short. I should be able to solve for what is C, right? Because when f is 0, I should get minus 2. So here, if I type in f of 0 is equal to minus 2, and so here we'll just plug in 0 over what we see next. So it'll be 0, arctangent of inverse tangent of 0 plus C. Oops, I forgot a little plus right here. Well, e to the 0 is what? It's 1, right? And then the arctangent of the arctangent of 0 is 0. Yeah, because tangent of 0 is 0. Because it's sine over cosine. Yeah. So this is plus 0 plus C. That means C is equal to negative 2 minus 1. So minus 3. So here we just solve for C here. We get C equal to 3. And then we can write in our and our function without a constant, because we solve for what that constant be, because I have an initial condition. The function at 0 is negative 2. So I know which function to use. And so here it'd be minus, no, plus 20 arctangent of 1, or the inverse tangent of the x, plus, minus in this case 3. Okay? And so if you're given an initial condition, i.e. the function value at a point, you can solve for the C. And so here's the function. So if I know a derivative of a function and a value at the function, I can tell you what the function was. If I only know the derivative of a function, I can say what the function is up to a constant, right? I don't know what the constant is, right? Because as we showed before, different functions will give the same derivative. Okay. All right, so let's do something. So find f if I know the second derivative of a function. And here I'm giving ourselves two initial conditions. So we should be able to find the f. So here, so f double prime. So f prime of x, and this one's actually in simplified form, so we don't need to do anything fancy. So what I'm going to do here is I'm going to just take the first antiderivative. So the first antiderivative will leave the 12. X becomes x cubed over 3 plus 6. And then here I have 6. So this is 1. So 1 plus 1 would be x squared over 2 minus 4. And here we're going to minus 4. And then here, I need to add an x. So maybe something that wouldn't be terrible to add to your little sheet here is if you just have a constant, it's constant times x, right? Because if I took the derivative of a constant times x, I just get the constant back. So for any constant, the antiderivative is times x. Now technically, that one's included in here because x to the 0 is 1. And so it technically includes the constant because I raised the 0 by 1 and divide by 1. Technically it's there, but I find it's nice to have it as a separate thing. All right, and then we're going to add plus c because I don't know what c is. right? And your book usually uses C for the first antiderivative and D for the second antiderivative. At least that's what it's showing me it's doing, right? All right, so let's take the next antiderivative. So here we take the next antiderivative. Oops. So when I take the antiderivative, I get rid of one of my derivative marks every time I do it. All right, so now when I take antiderivative, so I leave the 12, and then 12 divided by 3. Let's go ahead and simplify this real quick. This is just 4. This is just 3. Okay, so let's take the antiderivative here. So v4 times 3, if I raise that to the third, so v4 divided by 4 plus 3, because that's what 6 divided by 2 is, and x squared goes to x cubed over 3 minus 4. This goes to x squared over 2 plus c to the x, because here if I have a constant, I add an x to it, and then plus our next one, d. So d is just another arbitrary constant. So here we have our general form of the antiderivative. But I know 2 points, right? I know this point and I know this point. So we'll go ahead and plug this in. So let's plug in f of 0 and f of 1. Well, let's do it over here. So I just have room to do it. F of 0 equals to 4, which is equal to, well, if f is 0, or x is 0, this is 0, this is 0, this is 0, this is 0, so, which is equal to d. So I know what d is, right? D equals 4, right? D equals 4. Let's do f of 1. Well, f of 1 would be, oh, let me simplify this. Let me actually simplify this. This just becomes x squared. This becomes x cubed. This is minus 2x squared plus c plus d. That just makes our lives easier. So let's plug this in. So x to the fourth is 1 plus x 1 cubed is 1 minus 2 of 1 squared is 1 plus c times 1. And I know what d is. I know what d is. It's 4. So let's go ahead and just put that in. All right. So if I solve for c, I'll have c equal to, let's move this over. So -1. Actually, that just clears out. So I get c equals to, hold on. Oh, equals to 1. Ta-da. I was like, well, I'm doing something here. So if I move this over, so these two clear out. So 2 minus 2 is 0. And then if I move over the 4, I'm going to get -3 because -4 this side, -4 this side. I get this. So my actual answer here is f of x equals to, I'll kind of draw a little line so it has face, x to the fourth plus x cubed minus 2x squared. I know what c is. C is -3, so -3x. And I know what d is. D is 4. Okay? And so that's how you go through all that. All right, I'll leave that up for a second and take a drink. Any questions on this page whatsoever? Let me zoom out. Any questions on this? If you didn't put the constant, would your answer still be correct? In the WebAssign homework, the answer is no. Right? You have to have the constant. It is a solution, but it's not all solutions because they'll say find all solutions. So you have to be careful by adding the constant. Now, if it's on the written portion, I probably won't take off by like 0.5 of a point for it or something silly. Okay. For number 2, what's your question? Oh, in number 2. Yeah. No, for number 2, we actually solve for the constant, right? And so that is actually a decent part of the problem. So that is important to figure out what that constant is. Doesn't matter what order you plug in. Oh, for number 3, if I do the 0 or the 1, technically no, but if I do the 0 first, it should clear everything. It should clear away the you should only have one unknown, one equation and one unknown at that point. So it's just easier to do. Now, can you technically do it in any one? Sure. In my differential equation class, we usually I'm giving them 3 initial conditions, and they have a lot of constants and a much more complicated equations, right? So they have to use more advanced method to solve for it. Okay. Any other questions from this? On WebAssign, is there? Yeah. So on WebAssign, oh, does it matter which order you plug in? Yeah. So on WebAssign, it's going to be very clear. It's going to say what's it on WebAssign. It's going to give you something that looks like this, right? Or something close to this. It is going to say it says use the first antiderivative, so f of x, f prime of x. So if it gives you f double prime, just f prime of x, it says the first one, make it the c. It says the second one, make it a d. So in that case, for the computer, it matters. It matters a lot. Which one's C, which one's D, because I'll ask you which one's C, which one's D, and I'll expect it to be in that order. And then when you plug it, if it has initial conditions, though, it doesn't matter what way you use to label these because you'll solve for actual numbers. And this will always be a 3, this will always be a 4, no matter what you call them to begin with. Okay? Okay. All right, so let's look at the last part. So the last part of this is rectilinear motion, aka so an object moves along a single plane. So what does it mean by rectilinear motion? Usually it's kind of like you have a person who's standing here, he throws a ball into the air, right? What's the motion of the ball, right? And so it means in a single plane. That means in 3D space, I'm only working in a single direction. So a flat line. So it's not complicated like planetary motion. That's not rectilinear. That's a lot more complicated. But usually in this case, we use st for position, vt for velocity, and at for acceleration. So your book does a little bit of physics for a second, where the derivative of position is velocity, and the derivative of velocity is acceleration. Velocity is different than speed. Speed is the magnitude of the velocity, so the absolute value, right? Velocity, it makes sense to have a negative velocity. That means it's coming towards the origin or towards. So this has a magnitude and direction. It's either forward or back, right? And so, yeah, so we call this rectilinear motion. All right, so a particle moves in a straight line. So let's actually just get to used to doing this. Oh, often in these problems for motion closely, we assume gravity. G is a constant where we use 9.8 meters per second, or if it's in feet, it's 32 feet per second squared. Okay, so these are your two. It doesn't tell you that anywhere specifically unless you read the fine details, but we'll go through it. All right, so it says a particle moves in a straight line and has an acceleration given by this function, right? Find its initial velocity is this, and its initial displacement is this. Find the position function. So here I know the acceleration of an object. I know what its initial velocity is and initial position. So I want to know what is the function for this everywhere. So what do we do? We're going to say, well, v of t is the antiderivative of a of t, right? So if I take the antiderivative of this, I get this. So the antiderivative of a of t would be 6t squared over 2 plus 4t plus some initial condition c. Okay? And in this case, it makes a lot more sense to solve the initial conditions as we come to them, right? Because here I'm in velocity, so it makes sense to solve for c now, and so we'll do that. So 6 squared over 2, this is just the same as 3. Let's go ahead and just make that a 3. All right, so v of 0 is equal to minus 6 centimeters per second. So we're going to write everything in here as centimeters per second, just to keep it consistent, right? So minus 6 is equal to 3 of 0 plus 4 of 0 plus c. So what does that mean? C is equal to minus 6, right? So c here is equal to minus 6. So v of t, our velocity function, is 3t squared plus 4t minus 6. Okay. All right. So s is the antiderivative of t, and v is the antiderivative of a. So here we'll just have to take one more antiderivative. Okay. So v of t is the antiderivative of this, or s of t, which is the position function, is the antiderivative of this. So this becomes 3t cubed over 3, so take the antiderivative of t squared, plus 4t squared over 2, take the antiderivative of this, minus 6, we'll add a t to it, and then we'll add another constant here, d, just to keep in line with the book. We'll go ahead and simplify this a little bit. So this is t cubed plus 2t squared minus 6t plus d. That looked like a t. All right, so we know what the initial position is. It's 9 centimeters, so we'll just go ahead and leave it as 9. We'll plug in 0 here. Well, that's 0, that's 0, that's 0. So guess what? D is equal to 9. So usually if it's 0, this usually happens. And so here the position function is t cubed plus t squared minus 6t plus 9. Okay. And all this is given in centimeters per second. And so here, given a particle, and this one's moving in a straight line, right? We've given an acceleration, we figured out what the velocity must be, and given the initial velocity, we figured out what that constant is. And so we have what the velocity is. And then knowing the velocity of an object, we figured out what the position function must be. And knowing its initial position, we figured out what the little constant is, and then we got the position function for anything. All right, let's just do one more. All right, so a ball is thrown upward at with a speed of 48 feet per second off an edge of a cliff. It's 15 above the ground. What is the height above the ground t seconds later? When does it reach its maximum height? When does it hit the ground? Okay, so here we're going to answer some questions. So here we have some guy who's standing at an edge of a cliff, and he chucks a ball upwards. And he's just on the edge of a cliff. So he chucks the ball upward. The ball's going to come up. It's going to be under the force of gravity and come straight back down. We know this distance here is 432 feet. We know that he's thrown it up with a velocity of 48 feet per second, right? And I want to know, so find the height above the ground. So basically I want to know what's the ball's function. What is the function of this ball? What's the height function for the ball, right? That's all we care about. You might have thrown it a little bit of this speed, but that's going to remain constant, so you don't have to worry about it. When you get into a real physics class, you're going to do the y. You do the y component as one thing, and the x component is another thing. Since there's nothing acting on the x component, whatever x velocity here is, it'll just constantly move that over time until it hits the ground. And so here we're going to answer these questions. So this is very much like a physics test you'd have. So what's the acceleration here? So the acceleration here, what's the only force acting on this thing? The only force acting on this thing is gravity. And so we're going to be using this. So here, the acceleration of this is, so let's translate what we have here. No, let's go ahead and leave this. So the acceleration is equal to 32 feet 32, and because everything's in feet per second, so we're going to use gravity v. This is our gravity. Our acceleration here is gravity. Our v naught is equal to, our v of 0 is 48 feet per second. Our s of 0 is 432 feet. So here at time 0, I'm 432 feet above the ground, assuming the guy is of negligible height, right, when he throws the ball up. It says from a cliff's edge, so technically he's squatted down and then checked the ball upward, right? Technically. Oh, thanks. So I know the initial position, or the initial velocity. I know the initial position. And I know the initial and the acceleration. The only thing that's acting on it is gravity. So you just put that in. And is it pushing the ball upwards or is it pushing the ball downwards? Well, it's pushing the ball downwards, and so we want to make it negative in this case. So negative gravity. So here, v of t, we're just going to we'll go ahead and use, so here's our initial function. And so v of t would be plus t, so the antiderivative, we add a t, add a c here. We use our initial velocity. So our initial velocity is 48. And so this zeroes out, and so that's what c equals. So v of t with our velocity is minus 32. So our velocity at any point is minus 32t plus c, right? And then here we're going to do the same thing for s. We're going to take the antiderivative here, so it'll be minus 32t squared plus, oops, do I know what c was? Yes, it was 48. Plus 48t plus some d in this case. We're going to type in our initial position. Our initial position, so this is 0, right? So t of 0 is 0. T squared is 0. T of 0 plus d, so plus d. And that's all equal to 432 feet, or so 432 feet. So we have our position function. So the height of the ball in s, just because I'm leaving it in s right now, is, oops, did I forget something, guys? Yeah, I forgot divided by 2, right? This is t squared divided by 2. That's important. So here we get minus 32. Oops. So let's go ahead and clear out the 2 in this. So we get minus 16t squared plus 48t plus 432. All right. So now I want to answer 2 questions. Let's answer these 2 questions and give myself plenty of room. So when does it reach its maximum height? So what am I looking for? I want to optimize this, right? In order to optimize this, I find its derivative. Well, guess what? We know the derivative. It's right here, right? We already know it. We don't have to solve for it. Okay, so why is it so? Why is it 32? Let's answer all the questions. I got a couple questions I need to answer real quick. So here, if I take this antiderivative here, so minus 32, t goes to t squared divided by 2. And so when I divide by this 2, I get this. Why is it minus 32? This is gravity. Gravity is acting on the ball, right? Gravity. And so gravity here occurs at 32 feet per second. So these, I tell you this just because it comes up all the time. If the only acceleration acting on your object is gravity, so it's going to be negative because gravity is going to pull objects down, and we're going to assume that Earth or whatever terra firma you're on, right, is 0, and so it's always going to be a negative force because it's always going to pull downwards. So we're going to say y up is positive and y down is negative, right? Now, mathematically speaking, you can flip it around, right? It doesn't matter, but So we're starting at positive height, that positive thing, and so gravity. If I drop an object off a building, it's going to head towards 0, right, from a positive number. Now, technically, if I dug a hole in the ground, it's still going to head down, right, even though that's not positive, right? It's not going to head towards 0, but it'll still head down to the center of the Earth. Just gravity gets weaker and weaker and weaker. So it's negative because gravity is pulling downwards. Okay. All right. So here, when does it reach its maximum height? Well, we just take the velocity. Well, the maximum height is when its derivative is equal to 0, right? I want a critical point, right? And when its derivative equals 0, that's this point. So it is the maximum height, right? So when does it? It asks when. So we don't actually have to solve for what, but when. So here, if I solve this equal to 0, so when does v of t is equal to 0 when, so minus 32t plus 48, or it's not squared right now. So here, I'm just taking this and I'm going to solve it. When is that 0? Well, that's 0 when t is equal to 48. Oh boy. 48 is what, 1.5? Is that correct? Yes, okay, 1.5. At 1.5. And so at 1.5 seconds, so when does the ball, it reaches, and technically it's just right, it reaches max height at 1.5 seconds. If I want to know what that is, I just plug it into this function right here and then pop it out. Didn't ask for that, so I'm not solving for it. When does it hit the ground? So we want to know, when does it hit the ground? Well, that's when the function, the position function 0. So when is minus 16 t squared plus 48t plus 432. And you know what? I don't think this solves nicely, so we're just going to chunk it through Wolfram Alpha. Wolfram Alpha, I want to chunk some numbers. That's what you invented for. So let's go ahead and do those numbers I want to chunk through. I want to set this equal to 0. Where's my keyboard? Keyboard 0 equals minus 16 t squared plus 48 432. Wow. Okay. And so this is kind of nice because this will show us this right here, this graph right here shows us what's happening to the ball in the y direction. It goes up, it goes up, it goes up about 1.5 seconds, which we calculated, right? It hits its maximum height and then it crashes down to here, whatever this point is. And so, yep, I had a feeling it was going to be super ugly. So here's our super. Can I have the approximate form, please? Thank you. All right. So it approximately hits the ground 6.9083 seconds later. Okay. And so we just set that equal to 0. And so we get t is approximately equal to 6.9083. Now notice we have a negative 1, but we're not going to use the negative 1 because that's assuming we go backwards in time and the ball kind of floated up to the cliff. So that doesn't make sense. So we're only going to run time forward for this.